Before I introduce our esteemed speaker this evening, I would like to acknowledge the land and the Wiradjuri people that are the custodians of the land that we are coming to tonight, and to pay homage to the elders, both past, present and emerging. Okay, so like I said, there's a talk coming up in a few weeks' time on the 2nd of June. If you really enjoyed today and you can see there's a lot of fun stuff about to happen, then please come along. That one is by Professor Andrew. Let's see. I don't know what it's on about, but I'm sure it's going to be amazing. Did you know the planet's song?
The music of the spheres, I guess.
I believe there's a song about how to learn the names of the planets.
Oh.
Maybe. Anyway, come along and find out what it's all about. So tonight you're here to explore the ideas of special relativity, Einstein's special theory of relativity, and we're looking at light, space, and time. And tonight's lecture is delivered by Professor David Jamison, who I've known for quite a number of years now. And David works on methods for making new types of devices that use single atoms. So we all know how small an atom is. A single atom to store and process information in the ARC Centre of Excellence for Quantum Computation and Communication Technology. In this Physics Gymnasium lecture, it will introduce the mind-bending concepts of how space and time mix and match depending on your point of view, and that these strange phenomena show up all around us in everyday life. I mean, when Einstein came up with this stuff, it was science fiction, right? It came right out of a science fiction book because there weren't any movies back then. And yet you're about to tell us that this is real life. We experience it every day. Excellent. So could you please give David a warm welcome?
Well, Jacinta, thank you very much. I hope I can live up to that introduction. So Einstein's special theory of relativity, light, space and time. Don't anyone tell you, like it says in the VCE study design, that this only applies to things that move fast. Wrong. It applies to things that are moving really slowly. And as I will demonstrate later in this lecture, it applies to everything. It applies to chemistry. It applies to physics. It applies to everyday life. It applies to my wedding ring, as I will explain later in the lecture. So I want to echo Jacinta's acknowledgement of the original custodians of the lands of the Kulin, where we're attending this lecture tonight. And I want to also ask you to go out and buy our colleague Dwayne Hampshire's new book, The First Astronomers. Fantastic book, covers what the first Australians knew about the night skies. A real eye-opener, a fantastic book, highly recommended. So back to tonight's lecture. I want to talk about actually 3 great relativity principles. I think you need to know, first of all, what a relativity principle is and why we need 3 of them. I'm going to just try something here, Jacinta, to see if I can get rid of that. If I do that, nope. That was, we were on a roll there when that disappeared. It was supposed to. Sorry? Oh, yeah. That one? Oh, we've got it. Finally, after 2 years of trying. Okay, so 3 relativity principles. The first and greatest of which is Galilean relativity. And I'm going to have something to say about that first so that you're all up to speed with why we need a relativity principle. That was introduced way back in 1632 by Galileo, and it was developed further by Isaac Newton. And that seemed to be all you needed to know about physics, apart from a few untidy loose ends, which hadn't been tidied up, but it was only a matter of time. And then, much to everybody's surprise, Einstein came along and started tugging on those loose ends and unraveled the whole edifice of classical physics, of non-relativistic physics, as we'd say now, and introduced his new special theory. Are we okay? So I just press on. I think that means the UPS needs charging.
Oh.
You might need to grab an extension lead to get back online if it goes off. And then, of course, and that astounded the world when Einstein delivered that in 1905 and tidied up most of those loose ends. And then in 1915, he did it all over again with a new relativity principle, the general relativity principle. And we're not going to have time to say very much about that tonight, but I'll just mention it in passing because it's also really important in everyday life. So, everyday relativity. To explain all these things you see on this screen, you need Einstein's theory of relativity. First of all, permanent magnets operate via the laws of special relativity. Electromagnets, likewise. Electric engines in cars, trams, everywhere, that's all relativity. Down at the synchrotron in Clayton, the sync in synchrotron arises from relativity. If there was no relativity, it would just be called a tron without the sync. Out in space, this most peculiar object, a nearby yellow galaxy, and behind it there is a single quasar. But the light from that single quasar follows 4 different pathways through space-time to get to Earth. So we see 4 images of one quasar because space is highly non-Euclidean around the intense gravitational field of that yellow galaxy. You probably learned at school the circumference of a circle was equal to 2 pi r. Only an approximation, but you'll have to come to the university to learn the true formula. And of course, the GPS system. Where would we be without the GPS? Rumour has it that when the GPS satellites were launched, the conservative American generals who were in charge of the project didn't believe in relativity or Einstein's relativity. They were confirmed in Galilean relativity, and there was a big switch on the console. Einstein off, Einstein on. And when the first ones were launched, it had the switch set to Einstein off. The data came down. The positioning errors were tens of kilometres. The young work experienced guy was sent into the control room to flick the switch to Einstein on, and all the errors went away because Einstein was correct. Anyway, that's a lecture for another time. So in answer to the question that I posed, why do we need a relativity principle? Let me explain Galilean relativity, the first and greatest of the relativity principles. I've been a bit of a Galileo scholar over my career and made some amusing speculations that have gone, as they say in modern language, viral about Galileo's astronomical discoveries, but that's another lecture. But my colleagues at the University of Padua, where Galileo was once the professor of advanced mathematics, invited me to give a lecture covering some of Galileo's work in Galileo's lecture theatre, where he used to lecture advanced mechanics, as I said. And indeed, here at the University of Melbourne, I also lecture advanced mechanics, and I'm using the same PowerPoint slides that Galileo used in 1592, with a couple of updates. And so this is, you can see me standing in front of Galileo's podium where he stood to give his lectures. And there I am giving the lecture. And you can see up here what the ceiling of the lecture theatre looks like. And when I got back to Melbourne, I asked for our roof to be repainted in the same style, befitting giving lectures, but my request was denied. Okay, so getting back to the physics. Why do we need a relativity principle? Well, here you see the sun out in space. Here is the Earth, and here is the Leaning Tower of Pisa with Galileo on top of it. Now, this is only a legendary experiment. I don't know whether Galileo actually did this or not, but he probably did. So he took an object and he dropped it off the top of the Leaning Tower of Pisa. And the Leaning Tower of Pisa is pretty tall, and it takes about 3.4 seconds for the object to fall from the top until it hits the ground. And every time Galileo dropped the object, it always hit the ground directly underneath where he let it go, even though it took 3.4 seconds to travel the distance. And now, by then, Galileo was studying the Copernican model of the solar system, that said that the Earth orbits the sun and is not, in fact, at rest in the center of the universe. And he was a little bit worried about that because as you're sitting there, it's the overwhelming evidence of your senses that you are indeed sitting at rest in the center of the universe and everything else revolves around you. But in fact, that's not true. You are sitting on a sphere of rock that is rotating around its axis once every 24 hours. So you go from here all the way around the line of latitude of Melbourne, back to here once every 24 hours. You have to do about 1,300 kilometers an hour to get all the way around and back again in one day. Also, our planet orbits the sun. We have to go from here all the way around the sun once every 365.25 days. That requires our planet to travel at a speed of 30 kilometers a second. So Galileo worried, why do we not sense those enormous speeds? That's not inconsiderable. 30 kilometers a second, we'd be in Broadmeadows now, and then Melton, and then Ballarat, and whatever else is beyond that to the west. But we don't perceive it. So he said, there must be something going on here, such that when I release the shoe and the Earth travels sideways, a distance 101 kilometers in 3.4 seconds, the object retains the velocity it had when I let it go and only accumulated a velocity in the downward direction until it hit the ground. So at all stages during its journey, it continued traveling to the right at 30 kilometers a second and just accelerated downward under the pull of gravity, so that when you add those two things together, it ends up hitting the ground at the bottom of the tower. So 30 kilometers a second is 110,000 kilometers an hour on the speedo. So he came up with the idea that if you had a laboratory that was, say, at rest on Earth, you had a butterfly, you had an apple which you could drop, you had some kind of timekeeper, not a watch, it would be an hourglass, or his own pulse, more like it, that he used for timing things. Of course, he didn't have a torch, he might have had a candle. He did have also musical instruments. And he said, if you used all those things in another laboratory, which was speeding through the cosmos at very high speed, and you couldn't look out, could you do any experiments inside the lab to tell you were moving at high speed through the cosmos? And he argued you could not. The laws of physics do not depend on how fast you are going. And this was the first principle of Galilean relativity. There is no difference between these two scenarios, one at rest on the Earth, the other one moving at high speed. All the laws of physics are exactly the same. In other words, sitting here inside this lecture theatre, there is no experiment you can do, apart from looking out the window, to see if your laboratory is speeding through the cosmos at 30 kilometers a second and you notice the sun moving across the sky. And Newton in 1687 reaffirmed Galilean relativity and added to the fact that you need a force, which Galileo didn't formally define, to change your speed. But if you don't have any force, then you just continue the way you're going at constant speed. There you go. And this actually, Galileo, of course, didn't have a spaceship, but he considered moving at high speed on a ship, just to be accurate here, and wrote about that. And he also interviewed sailors that had fallen off the top of masts. They always hit the deck at the bottom of the mast, regardless of how fast the ship was going. Unfortunately for them, as they were falling, the ship didn't sail out of the way and they landed in the sea. They always still hit the deck after they fell. And this relativity principle is really important, because without this relativity principle, that the laws of physics don't depend on how fast you're going, there can be no heliocentric model of the solar system, because you have to be able to explain why all the evidence of your senses tells you you're not moving when all the evidence of the heavens tells you you are moving. So first you have Galilean relativity to make the laws of physics independent of how fast you're going. then you can displace the Earth from the center of the cosmos and set it in motion around the sun. And of course, there are a lot of things Galileo didn't know in the 17th century. Not only does the Earth rotate and orbit, it also, the whole solar system orbits the center of our galaxy at a speed of about 250 kilometers a second. And it turns out the astronomers tell us that the galaxy is plunging towards something called the Great Attractor at a speed of 7,000 kilometers a second. So it's just as well for good old Galileo, he couldn't measure any of those speeds. Otherwise, it would have truly blown his mind. It blows mine anyway, and I'm a great believer in Galilean relativity. So just to show you Galileo's reasoning and Newton's reasoning, I've got a bit of apparatus here that's actually very similar to the apparatus Galileo used to demonstrate Galilean relativity. He had an inclined plane, a flat bit, and another inclined plane. And he showed that by rolling an object down one side of the hill here, it would zoom across at constant speed and rise up to exactly the same height on the other side. Well, I'm just going to cool off a bit. Right, so so he could do experiments like this. So you get an object that goes down and then goes back up again. And in principle, if it wasn't for the hidden force of friction, would oscillate backwards and forwards. Then he said, well, what happens if we put a flat bit in the middle? Does it make any difference? And the answer is, no, it doesn't. It simply coasts at constant speed and still rises to the same height on the other side. And there's a wooden replica of Galileo's apparatus in various museums around the place, and it's quite interesting how simple the apparatus was, but how profound the implications were. We can use a ball bearing, less friction. Oh, marvelous. Less friction than a Hot Wheels car. Now, Galileo's reasoning then was, well, what happens if you get rid of the hill? Right? No hill. You set your vehicle in motion and off it goes looking for the next hill forever, but never finds it. So he reasoned this constant speed was just a natural state of motion. No external forces were applicable. The observers inside the car could do physics experiments as they coasted along looking for the other hill, entirely oblivious that they were moving. And you know that's true. In the old days, you know, I used to fly quite a bit, and time to have a drink. And if you were still parked at the gate, the steward would pour the drink into the glass in front of your nose and everything was well. The liquid in the bottle would fall out of the bottle into the glass and you could drink it. Or you could be in the aeroplane cruising at a very high speed. The steward pours the water out of the drink and out of the bottle, and is it going to fly back and hit you in the face at the speed of the plane? No, it just falls out of the bottle into the glass perfectly naturally, thanks to Galilean relativity. All right. So, Galilean relativity. You can't detect how fast you're going as long as you're moving at constant speed, not subject to external forces. Now, getting to the topic of today's lecture, Einstein's special relativity was a big upgrade of Galilean relativity. But remember, Galilean relativity had already displaced the Earth from the center of the cosmos and set it in motion around the sun. It was a huge transformation in the way humanity saw their place in the universe. So that's, what else do we need? Well, this is what Einstein did. And he did it in this apartment in Bern. I went and visited there a few years ago. This is Einstein Street. And if you turn and look up to the apartment, you can see Einstein looking out the window. It's now called the Einstein House. And this is his lounge room. It's only a 2.5 room flat, no kitchen, no bathroom, a front room, a bedroom, and a study. And this lace tablecloth is where he wrote E equals MC squared for the first time. Well, that's a special tablecloth. Lace tablecloth that had E equals MC squared written on it for not on the tablecloth, but in the notebook on the tablecloth for the first time. This is where he did all this amazing stuff in 1905 in this crowded, very small apartment with his first child. and that's looking out the window, nice geraniums, and it was a wonderful place to visit. But here's why we need to upgrade Galilean relativity. Einstein, even when he was very young, was fascinated by the magnetic compass. How does the compass work? Why does the compass needle always rotate and point in the same direction, regardless of the orientation of the case? Well, in order to explain that, we need to look at magnetism. Now, this is most properly a first-year physics subject, but in 5 minutes, I'm going to give you the whole majesty of electromagnetism in just a couple of key experiments. Now, the first experiment, Jacinta, can we go on to the electroscope? Do we need to switch something? Maybe I'll just go ahead. So here I've got an electroscope, a very this brass sphere, so that when I touch them on the top here, you can see the gold leaf deflects. Is that indeed what's happened?
Have you touched it?
Yep. Didn't happen. Oh, School of Physics cat's getting a bit tired.
A little bit.
Oh, gosh. Maybe the air is very damp in here.
Yeah.
Whoa, okay. Well, that shows what happens when you charge something up with the electrons on this brass sphere. The electrons redistribute themselves over the metal components, and the electroscope because the electron. Now, there's a modern version of that. Sorry, Jacinta, I'm going to switch over here. Where we dug out of an old photocopier. Don't do this at home, folks. It's dangerous. An old photocopier, a high voltage power supply, 15,000 volts, and connected it up to this flask, which has got two polystyrene spheres that have been coated with aluminium, connected by thin copper wires. And when I connect them to the 15,000 volt power supply, it sucks electrons off and makes them both positively charged. And sure enough, whoa, sure enough, they repel each other. The two positively charged objects repel each other. So this has been known for quite a long time. The word electricity was first coined by the ancient Greeks, who discovered static electricity like what I just demonstrated over there. But now, in the 19th century, the field of magnetism began to be explored. And let me show you how that works. Magnetism is a lot more complicated than just static electricity. How do I energize the beam? What I've got here is a very nice piece of apparatus. And I have to tell you, it's an enormous pleasure to be using this equipment again in person rather than just showing videos. Physics is the real world, not videos. Right, okay, sorry. So it's a beam of electrons accelerated out of a tube on my left through a high voltage. So they're traveling really fast with a velocity vector towards the door. Here I have a bar magnet. Let's get a big bar magnet. A big university bar magnet. And sticking out the end of this bar magnet, there is a magnetic field. Now watch carefully what happens when I bring the bar magnet in at right angles to the direction of the velocity vector, which is pointing towards Jacinta. Whoa, that's a complicated force. The magnetic field is sticking out towards you. The velocity vector is pointing towards Jacinta, and it deflects the beam down. I hope I've got that around the right way. And if I reverse the direction of the magnetic field, the deflection goes in the opposite direction. So here we have a force generated by this magnet, which causes a moving charged particle to bend. That's a little bit uncomfortable because that is a force that depends on how fast you're going. And I already told you that Galilean relativity says that the laws of physics do not depend on how fast you're going. So how are those electrons able to explain why they get deflected sideways? Because they're just sitting there at rest watching this apparatus go backwards at high speed, and yet somehow a mysterious force appears and makes them bend sideways. Their velocity is 0. So this was a bit of an untidy bit of electromagnetism that Galileo wouldn't have been able to explain. But don't worry, Einstein will. So that is a little bit strange. Thinking back on what's going on here, I've got these two charged particles in the flask sitting here on planet Earth, moving at high speed through the cosmos with all those velocity vectors I just explained. And the remarkable thing is that the magnetic field generated by this magnet is also generated by moving electrons. So in this magnet, there are moving electrons that generate a magnetic field that reaches out and deflects these other moving electrons. And I can show you those moving electrons in this apparatus over here. So what I've got here is a piece of magnetic material called gadolinium, not iron, it's gadolinium. That's not so cheap, this little tiny piece of foil attached to this string. And I've positioned it so that it's attracted to the poles of this very strong permanent magnet. Now, if you can't see that, let me turn the light on. Oh, did you see that? Turning on the light caused the piece of gadolinium to lose its magnetic effect. It's no longer magnetic, and it no longer was attracted by the magnet. Am I going to be able to reset that? Yes. Turn the light on again. Oh, and the light disrupts the magnetism. What's going on here? Well, it's pretty simple. Inside the gadolinium, there are electrons going around and around in orbits, classically speaking. Quantum mechanically, it's a bit more complicated. And those electrons are all beautifully lined up with each other as they orbit. That's the nature of gadolinium and iron. But the forces that keep them aligned are very weak. So all I had to do was shine some light onto it, heat it up. It disrupted all the alignment between the orbiting electrons, and so they were no longer working together and the magnetism was destroyed. So magnetism, like in an electromagnet, only occurs when all of the electrons are moving in the same direction. If they're just moving chaotically in all directions, it doesn't work, or it's not very strong. It's a different sort of magnetism called paramagnetism, but you'll have to come and do my second year thermal physics course to understand that. So with all these experiments, that was 5 minutes on the complete theory or the complete phenomena of electromagnetism that took humanity about 2,000 years to work out. So we have two different forces, the electrostatic force that applied here and to the two spheres, and the magnetic force that applied over there, where we have this moving charged particle that passed through the magnetic field of the magnet and got deflected, in this case, into the screen. Now, the reason why this is a little bit strange is, first of all, the magnetic force depends on how fast the electrons are going, and that's not compatible with Galilean relativity. But it's even worse than that, because here we've got two charged particles, which I've just charged up by connecting them to this power supply. The wires are a bit tangled. There they go. Now, these two particles are on the Earth, and we know the Earth is plunging through the cosmos at very high speed. So effectively, these are two magnetic currents running through space. Two electric currents running through space, that means they must be generating a magnetic field, because we already showed that moving electrons in our gadolinium generate magnetic fields. And so in addition to the electric force, which is repelling these two spheres, there must also be a magnetic force because of the motion of the two spheres through the cosmos that causes a slight twisting effect. Work it out. But no such twisting effect is observed in our laboratory. They behave as if they were at rest and not moving through the cosmos, and there's no associated magnetic field. Yet when I set a current moving through the atomic shells of a magnet or in an electromagnet, we do get a force. What's going on? There's something more complicated about electromagnetism that needed to be explained, and Einstein did it. Whoop, there they all go. Now, getting back to Einstein. Shall we do this one now? So Einstein's studied all of this. So here are two experiments that Einstein knew about. I'll just tell you what we've got here first of all. This is a coil of wire, many, many turns of copper wire, and it's connected to an electroscope here. Now watch what happens if a magnet moves through the coil quite quickly. Oh no, even not quickly. All right, as the magnet moves through the coil, it pushes electrons out of the coil, makes them flow through the circuit and deflects the needle on the galvanometer. So we're generating electricity, but only if the magnet is moving. So the moving magnet pushes the stationary electrons out of the wire and makes them flow around the external circuit. We need a law of physics to do that. But let's do moving the coil instead. Hold the coil fixed, hold the magnet fixed and move the coil. So now we have moving electrons in the magnetic field, moving electrons inside the copper wires, moving relative to the magnetic field of the magnet. So this is very similar to what we were doing over here, where we've got moving electrons through a vacuum, not in a wire, moving through the magnetic field of the magnet. And that also causes the electrons to be pushed out of the wire and go around the circuit. So just as, great, that's terrific. Let me go back to the computer. Wow, it's hard to remember which one's which. Oh, good on you. All right. Oh, thank goodness. Okay, so here are the two experiments. Here's the first one. Oops. Here's the first one. The moving coil goes over the stationary magnet. The law of physics to explain that is F equals QV cross B. Never mind, it's the Lorentz force. And the bottom one is where the magnet moves through the coil. The coil is at rest. The moving magnet changes the magnetic flux through the loop, and the magnetic flux gives rise to an electric potential, which pushes the electrons out of the wire. And so Einstein knew this. He'd learned it in first year at university. Everybody knows this. But Einstein was greatly troubled by the fact there were two completely different laws of physics needed to explain this. One was the action of the magnetic field on the moving electrons, and the other one was the action of the moving magnet on the stationary electrons. So here he said something like, Achtung, there does not need to be two laws of physics here. Only relative motion is important. That was his first observation. Now for the second. When he was very young, he wondered whether he could catch a beam of light. So here's what he thought. He didn't know about photons in those days. He got the Nobel Prize for inventing them a few years later. Here's a beam of light traveling across the front of the lecture theatre. And Einstein wondered whether he could run after it and catch up. So in other words, this is why you should never come late to a physics lecture, by the way. You might get a laser in your ear. Just because I forgot that when we've got the doors open, I'm doing it this way rather than that way is my custom. So he said, okay, maybe I could run after those packets of photons and catch up to them and see what they look like and run along beside them and study them as they're traveling through space. Now, so there goes a beam of light past James Clerk Maxwell, who happens to be nearby. And Maxwell said, okay, let's consider, this is before Einstein, what exactly light is. And then Einstein asked the question, can you catch a beam of light later, about 40 years later? So Maxwell said, a beam of light we know that a beam of light travels really fast, about 3 by 10 to the 8 meters per second. We also know from all the mathematics that he'd done that you could have a thing called an electromagnetic wave of a self-sustaining pair of electric and magnetic fields that oscillate and propagate off by themselves to the edge of the universe. And that sort of electromagnetic wave travelled, according to his calculations, at 3 by 10 to the 8 meters per second. So he said, it's surely a beam of light that I've just modelled as a coupled pair of electric and magnetic fields. And it's not a beam like this. This is what a sound wave does. It's a pressure wave that oscillates in the direction of travel through the air. It's a wave like this, where the oscillation of the fields are transverse to the direction of motion. I'm only doing this because I love this bit of 19th century lecture demonstration apparatus. And when I stop turning this, I have to put it away for another year. So I'm sorry, I'm just going to keep turning it for a little bit longer because it's so nice. This is Maxwell's electromagnetic wave. I'm just showing you the electric field. You have to imagine there's a magnetic field oscillating like a sine wave at right angles to the direction of this electric field. And the two fields sustain each other and propagate through space at the speed of light because it is light. Oh, put it away again. All right, now, Einstein didn't have any fast vehicles in the late 19th century, but you could imagine hopping on a very fast spaceship and chasing down a beam of light to study it. So knowing what Maxwell taught us, that this is the mechanism of light, let us try and answer Einstein's question. There are basically only two possible answers to Einstein's question. Can you catch up to a beam of light? Well, maybe light, whoops, I've gone back to the danger mode. Oh, sorry, I just changed ends of the theatre here. Maybe the beam of light that he's chasing behaves like a tennis ball. Okay, and we know how tennis balls behave. The speed of the tennis ball depends on the speed of the source and the observer. So, for example, if I hit a tennis ball in this lecture theatre, I can run after it and catch up to it. Also, I can make a tennis ball go faster by running while I hit the tennis ball because my velocity adds to the speed of the tennis ball. Or in other words, I can make the light go faster if it behaves like tennis balls by doing this. Ah! Right? Wow, that's faster than the speed of light. It gave it a push, right? Wow, that's probably twice the speed of light right there. Maybe. No, it's wrong, of course. You know that. Or could I make light go slower by doing this? Ah, well, that's only half the speed of light because it was going backwards when I launched it. So does light behave like tennis balls? Well, the answer is it doesn't, because a whole lot of experiments were done to try and answer that question, and it didn't work. So the only other thing that people knew about was sound waves, and people knew that the speed of sound depended only on the nature of the medium through which the sound was travelling. So, for example, here we are in this room, the air carries my sound to you. If I want to get my words to you more quickly, I could run towards you while I'm talking and give the sound a boost. Or I could, does that work? No, it doesn't, because I dump the sound into the air and it travels through the air at about 300 meters per second, regardless of how fast I'm going, because it only depends on the speed of the medium. And in fact, I can make a yell, hello, and I can run after it, overtake it, hello, oh, I heard it again, because I could run faster than the speed of sound. In theory, work with me here. So that's how sound behaves. It depends only on the speed of the medium, not the speed of the source or the observer. So a further question in answering which of these two are correct, sneak preview, neither of them are, maybe we could use light to break Galilean relativity, and by using light, measure the speed of our laboratory through the cosmos. So that's what Einstein tried to do. So here are just to make sure we're all on the same page, here's the results of the tennis experiment, the tennis ball experiment. So here is a tennis player. I'm just going to take this down a bit. There's the tennis player hitting the tennis ball. The tennis ball heads off to your left at 100 kilometres an hour, and the observer watches it go past and clocks the speed. Yes, it's 100 kilometres an hour. And there's a Cartesian coordinate system X, Y here to help them make measurements and compare them. There it goes. Right, that's Galilean relativity. But now the tennis player is superglued to the roof of this car. And this car is heading to the right at a speed of 100 kilometres an hour. There's a new Cartesian coordinate system, X prime and Y prime, attached to the tennis player. So now when the tennis player hits the ball, all he does is cancel out the speed of the car. 100 kilometres that way minus 100 kilometres that way gives you 0. But the tennis player is not unhappy. He sees the tennis ball receding from him at the usual speed of 100 kilometres an hour. But you can see the speed of the tennis ball has been communicated to the speed of the car. And the observer on the ground says, well, I see the tennis ball resting on the ground because all you did was cancel out the speed of the car when you hit the tennis ball backwards. There he goes. So if we look out into space, we can see exactly this experiment being done all the time. It turns out most stars in the sky are actually double stars or more, not single stars like our sun all by itself. This is a pair of stars that can be seen from Earth over here, not to scale. And we're looking in the plane of their orbit. And in this instantaneous snapshot, the yellow star is heading towards Earth at the speed v, and the red star is heading away from Earth at speed minus v. They've both got equal mass and they're orbiting around their common centre of mass. So if light behaved like tennis balls, then the yellow light would get a boost and would travel at c plus v, c being the speed of light, celerity means fast, and the red light emitted from the red star moving away from the Earth would travel at a reduced speed, like the tennis player noticed, or the observer on the ground noticed when the tennis player hit the ball backwards relative to the direction of the car. And that would mean these two beams of light crossing the immense gulf between the stars and the Earth would get out of sync. The yellow light is going faster than the red light. And then it gets even more complicated because the yellow star orbits around and takes the place of the red star and starts emitting light that's going too slow, and then goes back to where it was in the first place and emits light which is going too fast. All the light signals would get out of sync. So when you looked at this double star system, some of which orbit each other really fast, instead of seeing a nice orderly pair of stars going around each other, you'd see chaos. You'd see 10 stars going forwards, backwards in every which way as the light signals all got out of sync and mixed up as they crossed the immense gulf between the stars and us. Needless to say, you don't see that. When you look at a pair of double stars orbiting each other, you see them orbiting two stars orbiting each other in a perfectly orderly way. No splitting up into different images, going forwards and backwards, all sorts of chaotic stuff. So we have to conclude, therefore, that light doesn't behave like tennis balls. No matter how fast the source is going, the speed of light is always c. It never accumulates the speed of the source, or the observer for that matter. So that's exactly like sound. So, okay, it looks like light behaves like sound waves. Let's remind ourselves of how sound waves work. Here's the late and much lamented Concorde travelling through the sky at twice the speed of sound. Now, early on, there were problems with the rudder and occasionally bits would break off. So it pays to have an observer superglued to the back of the aeroplane, keeping an eye on the rudder, and periodically would shout a report to the pilot. She'd stick her head out the window, "Everything okay down the back here?" And the pilot would be listening and would never hear anything because the sound waves from the observer are dumped into the air and propagate to the right at the speed of sound, Mach 1, but the aircraft is flying to the right at Mach 2. So it's leaving the sound behind. And it's only after the aeroplane reaches its destination as it's parked at the gate that finally the reports from the observer trundling through the air at the speed of sound gradually catch up and the pilot will hear the reports. So, is this how light behaves? Well, there's the velocity vector of the light in the observer frame, minus cs, where cs is the speed of sound, about 1,000 kilometers an hour in round figure terms. So in answer to the question, does light behave like that? Here's the experiment that was done in the late 19th century to try and detect whether light behaved like that. So we're already on a very fast object, the Earth. Back in the late 19th century, nobody knew about galaxies. So the only velocity vector they knew was the orbital velocity of the Earth as it orbited the sun, and that was known to be very large. So here's the trick. You imagine that light propagates through space in a medium analogous to air for sound, which was called the ether. It was invented specially to act as a medium for carrying light waves from place to place. A terrific 19th century idea, steampunk, in fact, really. So here's the Earth orbiting through the ether that carries light around, because everybody knew that you can see light from distant stars. So the entire universe must have been filled with ether carrying sound waves, beg your pardon, light waves from place to place. So the idea was that this ether wind, this ether would create a very strong wind, like when you put your hand out the window of a car that's going at high speed. You feel the air rushing past. So this ether must be rushing past as the Earth plows through it. And the guys who did this, Michelson and Morley, set up an experiment on a big block of granite floating on a tub of liquid mercury so they could rotate the apparatus. And they basically did as follows. They sent a beam of light in the direction of the Earth's velocity vector. And they expected, after they launched the light into the ether, the Earth would rush to catch up to it. So the speed of light in the horizontal direction in this diagram would be slightly less by the speed of the Earth, 30 kilometers a second. And then to compare, they sent a beam of light at right angles to the velocity vector of the Earth. And for technical reasons, they reflected the beams and brought them back together again and created an interference pattern. And the interference pattern was exquisitely sensitive to differences in the speed of the photons on the moving Earth. And after they completed their experiments, which they repeated over and over again, not only in the basement of the physics building, but on the tops of mountains, out in the ocean, anywhere they could, they always got the same result. Michelson wrote in his lab book, we saw no result, regardless of the orientation of our apparatus and which direction the light went. It's as if the ether does not exist. And this was deeply shocking because light didn't behave like tennis balls, as the double star observation showed, and it didn't behave like sound waves either. There did not seem to be a medium carrying light from place to place. The speed of light was independent of the speed of the source, the Earth in this case, and the speed of the observer, the Earth again. So let's sum up. Does light, an electromagnetic wave, behave like tennis balls? This is how tennis balls behave. The answer is from Galilean relativity. You transform between the x prime and the y prime coordinate systems like this, and it turns out it didn't work like that for light. And both of these observers got the same answer for the speed of light, c, 3 by 10 to the 8 meters per second, even though they were in a state of relative motion. So let me do a thought experiment to bring this home, because this is really shocking and you should be appalled at this, because there goes the old Galilean relativity. Imagine instead of being at rest here on the surface of the Earth in the Hercus Theatre, we're in a spaceship and we were heading towards the sun at very high speed, half the speed of light. And I've opened the window in the side of the spaceship there, in the direction, in the front of the spaceship, and you can see the sun out the window when I lower the blast shield in the traditional way with that big red button on the console. And we can see the sun, and we're plunging towards it at half the speed of light. From the diameter of the Earth's orbit, we'll be there in 4 minutes. So we haven't got long to do this experiment before we crash into the sun. But we see the light from the sun shining through our window. There it is. It's shone through the window. And let's put that at x equals 0. And I start my stopwatch and I time how long that photon takes to pass through my spaceship and out the back window and continue on its way. Right? I know how far it is across my spaceship. I've recorded the time. I take the distance divided by the time to get the speed in the traditional way. And what do I get? 3 × 10⁸ meters per second. Even though I'm heading towards the sun at half the speed of light. Because the speed of light doesn't depend on the source or the observer. It's always 3 × 10⁸ meters per second. Now I back up the spaceship and I open the back window and I'm now retreating from the sun. I'm looking at it in the back window and I see the sun receding from us at, say, half the speed of light. There it goes off into the distance. But once again, I let a photon in. I let the photon propagate across the length of my spaceship and come out the other window. And once again, I know how far it is across my spaceship. I've got accurate clocks to time how long the flight time is of the photon. I take the distance over the time. What do I get? 3 × 10⁸ meters per second. It doesn't matter which direction I'm going or which speed I'm going. The speed of light does not depend on the speed of the observer or the source relative to my spaceship. This is special relativity. The speed of light does not exist because there's a medium like there is for sound against which you can measure your speed. There is no medium for light. This, even today, as an esteemed professor of physics, I think Jacinta said, thank you very much, I get more correspondence from members of the public who said, I want to argue with the second postulate of Einstein's theory of special relativity that said that light doesn't depend on how fast you're going because it's against common sense. Right. Who cares what your common sense is? The universe doesn't care how a small biped on some insignificant planet in a backwater of the Orion spiral arm of a nondescript galaxy 13.5 billion years after the Big Bang thinks. The universe works the way the universe works, and I'm glad it works like this because it's given me a job teaching this stuff for the last 30 years. Right, there we are. There's the experiment. I'm a bit conscious of the time, Jacinta. All right, so I just got another 10 minutes. Is that okay? Okay, I just want to do 2 last demonstrations to show you how strange this is. Here in the lecture theatre, I've got this very nice clock that Steve, our lecture demo guy, made for me. It's a very simple clock. It simply consists of 2 parallel mirrors into which I can inject a beam of photons. Oop. All right, I've put the incense in the wrong spot, but anyway, you get the idea. I can inject a beam of photons into the 2 mirrors and they can bounce up and down. And let me just move that quickly. They can, it's terrible, that incense. They can bounce up and down between the mirrors, up and down. I can measure how far apart the 2 mirrors are. I know how fast the light goes, and this is a perfectly good clock. But imagine looking at this clock ticking away from a different vantage point. Instead of sitting here in the lecture theatre and watching the photons bounce up and down, imagine you were parked in a spaceship at rest relative to the sun and the Earth went past. So during the experiment, the Earth moved sideways, greatly exaggerated the amount here. And so the photon, instead of just moving straight up and down like it is in the resting spaceship out at rest relative to the sun, it has to move this long diagonal path at the speed of light. So the spaceship sees the Earth clock ticking slowly because the photons have a long way to go because of the sideways motion of the Earth. The moving clock, therefore, ticks slowly. This is an easy clock to analyse, but any sort of clock will give you the same result. It's just the maths is much more difficult. This is time dilation. The spaceship at rest sees our moving clock tick slowly because the photons have got longer to go compared to their clock at rest in the spaceship. And there's the maths. That'll be on the exam. Right. Now, even more distressing is the strange behaviour of rulers. When I fly, I always like to take my Geiger counter with me so I can measure the cosmic ray flux through the aircraft 10 kilometres above the surface of the Earth and entertain my fellow passengers, which seems strangely disinterested. But sufficient to say, towards the top of the Earth's atmosphere, unstable radioactive particles called muons are constantly being created by the cosmic ray bombardment of the gas atoms in the atmosphere. Some maybe around 4,800 metres up. Now, these muons live on average for 2.2 millionths of a second. So even if they're created travelling downwards at the speed of light, which they're not, they're going a lot slower, in 2.2 millionths of a second, they've only got time to travel 660 metres before they have to decay. If they're at rest in the lab, you time how long it takes them to decay, it's 2.2 millionths of a second. They're moving downwards after they've been created by the nuclear reaction at the speed of light. They can travel a maximum of 660 metres. So there's no way the muons can live long enough to reach sea level. And yet here in our third year labs, we've got a prac where they measure the muon flux at sea level. And there are heaps of muons. Why? Because the muons are moving really fast. Their clocks are ticking really slowly. So the muon lives long enough to get to sea level, even though if you measure it at rest in the lab, when it's not moving, it decays in 2.2 millionths of a second and will never reach sea level. The fast muons travel fast, their time runs more slowly, and we can check it in the lab here. But more problematic is what happens from the point of view of the muon. So I've changed the colour of the screen, so we're now sitting with the muon at rest. And the muon looks across and sees the tourist information sign. Oh, look, there's a very fast mountain going past. And according to the tourist information sign, it's 4,800 metres high. Too bad I'm not going to live long enough by my watch to reach the bottom of the mountain, to see the bottom of the mountain go past. Yet the muon lands in the detector at sea level. Is the tourist information sign wrong? No, it turns out the mountain is too short. It's only 600 metres high, not 4,800 metres high. Because moving objects shrink along their direction of motion because of relativity. And here's the mathematics, and there's the result. And that's all to do with the slow ticking clocks. Now, an important number here is the gamma factor. This is the last point, Jacinda, and then I'll stop. The gamma factor tells you by how much the objects shrink or by how long the clocks run slowly. It's 1 over the square root of 1 minus v squared over c squared, where v is the relative speed of the two objects. Today, we've detected protons that have come in from outside of our galaxy and collided with our atmosphere and created a shower of subatomic particles that we know were protons that have been accelerated to such an enormous speed that they're travelling just slightly less than the speed of light, and their gamma factor is 10 to the power of 10. Extreme time dilation, extreme Lorentz contraction. So here's our galaxy. It's 100,000 light years in diameter. There's the very fast proton that we detected colliding with our atmosphere. It will cross our galaxy, travelling at the speed v, just slightly less than the speed of light, in 100,000 years, because the galaxy is 100,000 light years across and the proton's going roughly at the speed of light. But what does the proton see? The proton is at rest and it sees this very fast galaxy going past at just slightly less than the speed of light. With a gamma factor of 10 to the 10, the galaxy is only a width of 0.7 of the radius of the Earth's orbit, because of the Lorentz contraction. The galaxy goes past in 5 minutes in the reference frame of the proton. I really wish I knew how to accelerate myself to a speed such that I have a gamma factor of 10 to the 10. Because I could tell you, I'll be just back in 10 minutes. I'm just going to pop out to the other side of the galaxy, and that'll take me 5 minutes and 5 minutes back, and I'll be able to report back to you what it looks like. Why should you not wait for me to return? Yeah? No, modern technology will keep you alive. It'll take 200,000 years for me to get back, according to your clock. Better make sure your batteries are well charged, Grandpa. But that's the way the universe works. So the universe seen by a photon is even more disturbing because photons travel at the speed of light. So here's my impression of a photon stored in the excited atom of a gas in the atmosphere of Alpha Centauri, about to launch itself towards Earth. Are you ready? Okay, I'm in the excited state of the atom. The atom decays. The photon emerges from the atom at the speed of light. The diameter of the universe contracts to 0. The photon steps across into the retina of the astronomer's eye. The universe re-expands to its original size. Whoa. Because you heard that in a physics lecture, it's true. Well, with that, folks, I might wrap it up. I hope I've convinced you that relativity is true. Oh, and the final demonstration. Let's do this final demonstration. I just wanted to convince you that relativity works even for things that go very slowly. So here I've got 2 aluminium wires. They're very light. And we can use this beast, this big power supply, to put in a large current through these wires that'll generate a magnetic field. And the electrons are moving through this wire at a speed of about 0.1 millimeters per second. Let me demonstrate that for you. I'm doing it. Okay, that's how fast the electrons are going. But that speed has a gamma factor associated with it. The gamma factor is almost exactly equal to 1, but it's just slightly greater at about the 20th decimal place. That causes a distortion of the charge balance in these 2 wires because the electrons see the aluminium ions moving in the opposite direction and they contract. And that charge imbalance causes a force, an electric force. This is what you would call magnetism when you study it at school. Don't question your teachers and say it's only relativity and it's an electric force. You're too soon for that. But that is a manifestation of relativity, the Lorentz contraction, the gamma factor for an object that's moving only at a fraction of a millimeter per second. Can we reverse the current? Okay, oh, that's going to stand right back. So we now have reversed the current in one of the wires. All right, so now the forces should be in the opposite direction. Oh, the wires are touching and they're short circuiting and they caught fire as usual. And that's the end of the lecture. Thank you very much for your attention. Thank you very much. That's perfect. Perfect.
I don't have much more to say, but a big thank you to Dave. Very patronizing again.